Last time we were here, right? We have discussed about the relationship between the potential energy and the conservative force. Okay. Now, given the potential energy, we can derive the conservative force by taking the derivative. Okay. So if you are given such a potential energy, you can differentiate the potential energy with respect to x to get the force. Now, please be reminded that there's a minus sign that goes before the du dx. The force is the minus du dx. So when you take the derivative, don't forget to add a minus sign to get the force. Okay, so that is the idea. So if you have, for example, a spring, then the potential energy goes up with the extension as a quadratic function, half kx squared, right? So when you differentiate u with respect to x, you get kx. And after adding a minus sign, you get the force as minus kx, which is in a negative x direction. So the slope goes up, but the force pointing backwards. Okay, so you can imagine if this is a marble rolling down a hill. Okay, so the force is always directed to the directions of decreasing u. So you can imagine this marble to be rolling down. So the force will be directing it towards the direction of decreasing the potential energy. So it's in negative x direction in this situation. And similarly, if you have a potential energy, the gravitational potential energy near the surface of the Earth, which takes the form of mgx, then after taking the derivative and adding a minus sign, you have the force equal to minus mg, which is of course the downward force of gravity. Okay. Now, if you have this expression, when the body is located at a very far point, which is very far away from the Earth, then the near Earth surface approximation would not hold, and you have to resort back to the exact formula for the potential energy between two gravitational body, and that is minus gmm over r. And when you take the derivative, you add the minus sign, you go back to Newton's law of universal gravitation. Okay, so again, you imagine a marble here, and the marble will roll down the slope, so the force will be directed towards the direction of decreasing potential energy. So remember this relationship. Okay, don't forget the minus sign. You just remember the marble rolling down the mountain, and that is a simple way to remember it. Okay. Now let's talk about equilibrium. Let's talk about equilibrium. Now, what is called equilibrium is a point. We call the equilibrium position is a point where the conservative force acting on the body is zero. Okay, and that's corresponding to the conservative force, which is given by minus du dx is equal to zero. Now, when you learn elementary calculus, you understand that whenever the derivative of u is equal to zero, then either u is a maximum or a minimum, right? It's either a maximum point or a minimum point. At these two in these two situations, the slope of the curve is equal to zero. So the du dx is equal to zero, but that corresponds to the force, right? So that means the force at these 2 points, they are equal to zero. So there are two different situations. The first situation is that the equilibrium position corresponding to a minimum position of u, and the other situation is the equilibrium position corresponding to the maximum value of u. So we discussed these two situations respectively. Okay. Now we are interested not exactly at the not only exactly at the equilibrium position, but we are concerned with what would happen if the object is now slightly dissipated away from the equilibrium position. Now let's take the case of the minimum position of the potential energy. So this is a value here. Okay, the curve is the curve of u versus x is concave upwards, and here we have the minimum position, a position where the u is a minimum, and that corresponds to du dx equal to zero, right? So the force here, at this position, the object is not acted by any force. Now, if we imagine the object is slightly displayed away from this position, say to the left, say to the right, okay? If we display the object slightly to the right, then according to this picture, right, you can simply draw a tangent, okay, to the curve. And the force will always be pointing to the direction of decreasing u, right? So it points to the left, right? So that the force will then what? Will then tends to move the object back to its equilibrium position. Okay, so when we slightly display the object to the right, the force acting on the object will tend to move it back. And similarly, if we move the object to the left, if we draw a tangent, this force is the negative of the slope of this tangent, and that means the force is to the left, is to the right, right? And so the object will also have a tendency of going back to the equilibrium position. So that means no matter how we displace it, the force due to the conservative force will always tend to move the object back to its equilibrium position. Okay, so that's a stable equilibrium. The stable means it will not affect that the equilibrium will not affected by small disturbance. If we small disturb it slightly, it will go back, simply go back. Okay, so that's why it is stable. So in principle, if you have a slight small displacement above this equilibrium position, the object will not move away. It will stay close to this equilibrium position, just oscillate about this equilibrium position. So that's why it is called stable. Okay. Now, how about if the potential energy is a maximum? Again, we have du dx equal to 0. There's no force there. The slope here is 0, right? But it is very different from the stable equilibrium. If we displace the object slightly to the right, we draw a slope, we draw a tangent to the curve, and the force always goes in the direction of decreasing u. So the force is now to the right, right? And it will further move the object away from the equilibrium position. And similarly, if we displace the object to the left, we draw the tangent, and we find that the force will also display the object further away from the equilibrium position. So that means it will roll down the slope, right? It will not be staying in the equilibrium position anymore. Even if you have a very small displacement, the force will make it farther and farther away from the equilibrium position. So it just roll down the slope. You imagine you have a bowl. You rise with a bowl. You invert it, and you put a marble at the top. That will not be stable because the marble will simply roll down along the slope. Okay, so that is an unstable equilibrium. Unstable equilibrium means it is not possible to make it stably rest at this position. Even a very small displacement will move it away. The object will simply move away from the equilibrium position. Okay. Now, so an important inference is that whenever the potential energy is a minimum, that corresponds to a stable configuration. So the system always like to settle, if you say like this, like to settle itself in a minimum position for the potential energy. And that is why it achieves a stable equilibrium there, okay? Now we discuss about the conservation of energy, okay? Because we now know how to calculate potential energy, so we would like to discuss an important principle of conservation of mechanical energy. Now let's consider this situation. We have a force acting on a body of mass m on a smooth horizontal table. So the force will thus work, right, on the body. So where would the energy go? Okay, in your high school physics, you have learned this before, right? You know that the force does work on the object, and the energy transfer to object goes to what? because now the object is not affected by any other force, just only one. So the force work done by on the object goes to the change in kinetic energy. Suppose there's no friction to oppose the motion, so the force will deliver the energy to the body, and the body will have a change in its kinetic energy. Okay, now we are going to derive that. You have seen a similar derivation before in your high school study, but now we are using calculus to do the same derivation. Now let's see how we do it. Now we further suppose that at a certain instant, the object is at the position x1, where its initial velocity is v1. And after a while, it moved to another position, which I call x2, where its velocity is v2. Okay, so we are going to relate v1, v2, x1, x2 to the work done, and also to the change in kinetic energy. Okay, so let's see how we are going to do it. And of course, we will start with Newton's second law, F equal to m dv dt, right? This is the starting point. And then we multiply the equation, both sides of the equation, by a factor of the velocity. So it becomes mv dv dt equal to fv, okay? Now here comes a trick, okay? Now we are moving the differential again, okay? We move the differential dt to the right-hand side of the equation. So the right-hand side now will become fv dt, okay? Now, but what is v dt? Let's see what is v dt. We know that the velocity is given by the time derivative of the position, right? The velocity is dx dt. Is that right? So if we move the differential dt to the size of the velocity, we get dx as v dt. Okay. Now this is nothing but the usual relationship between the displacement and the time taken. If the time interval is sufficiently short, then the velocity doesn't change much, right? The velocity essentially is a constant in a very small time interval. So you multiply that time interval with the velocity at that instant will give you the displacement, will give you a small displacement in that time interval. That is the physics behind, right? Now, so if I multiply v with dt here, I just get dx, a small displacement of the object in the time interval that dt, okay? And the corresponding change in the velocity will be dv. That is reflected on the left-hand side, okay? So that means the force after moving the object by a small distance dx, there will be a small change in the velocity. There will be a corresponding small change in the velocity. Now, but what is this on the right-hand side? What is f dx? F dx is exactly the work done, right? The force multiplied by a small displacement is the work done in that small displacement. Okay, it's work done by the force in that small displacement. So naturally, we will try to integrate it because we would like to know the total work done by the force from the initial position x1 to x2 to the final position x2. So we integrate the force over the displacement from x1 to x2. And correspondingly, the integration on the left-hand side will be integrating the velocity, right? Because the left-hand side only consists of the velocity, the factors that involve the velocity. So we naturally will involve an integration from the velocity from the initial velocity of v1 to the final velocity of v2. Okay. Now notice that the lower limit x1, the position corresponding to the velocity v1, and the final velocity, final position x2 corresponding to the final velocity v2. Okay. So when you integrate the quantity on both sides, make sure that the limits are corresponding to the same position. What happens at the same position at the same time? Okay. Now, I think you know how to do this integration. Integration of V is V squared over 2. And when it evaluates at the upper and the lower limit, I just got half mv2 squared minus half mv1 squared. Okay. Now, but the left-hand side is what? The left-hand side is the work done. The work done by the force from x1 to x2. And this is equal to the difference between these two quantities. Okay, which involve only the square of the velocity and the mass, right? And so we would like to define, now this is what we define. Actually, after working through this step, we discovered that this object, this half mv squared, should be identified as a kind of energy. And that is exactly what we call the kinetic energy. Now, why do we do this interpretation? Because we know that the left-hand side is work done. I deliver some energy to the system, right? So by the work energy theorem, if I want to maintain the work energy theorem, I would consider this energy to be causing some kind of energy change. The work done must be causing some kind of energy change. And so this is natural to interpret this term, half mv squared, as a kind of energy that associated with the motion of the body, and that is the kinetic energy. So this is the final kinetic energy, half mv2 squared, minus initial kinetic energy. So I can rewrite this equation as the work done being equal to the change in kinetic energy. I deliver some energy to the system by the work, and it goes to the kinetic energy increase. Okay. So this is again a special case of the work energy theorem. It says that the work done by the force goes to the change in the kinetic energy of the body. Okay. Now, in the previous example, we haven't mentioned about this, right? We simply assume that the object is moving slowly by the external force, right? When we talk about potential energy, we assume that the body is moved by the external force slowly. So it doesn't have a change in kinetic energy, or the change in kinetic energy is negligible. Okay, imagine when we talk about the conservative force, right? We talk about a Superman, right, moving an apple from infinity very slowly to the final destination. So the velocity is negligible. We assume the process to be done very slowly. Okay, and we attribute the work done by the force to the change in the potential energy. Okay, now in this cases, the force, F is the only force acting on the body. So we don't have other conservative force. So that means the work done by the force F now goes to the motion, now increase the speed of the body, and it's become the change in the kinetic energy. So this is another situation of the work energy theorem. Okay. Now, so far, what we have discussed were very general situation. We haven't imposed any constraint on the force F. The force F is general. Okay, you may apply this equation to any kind of force. Okay, the force F may be conservative, non-conservative, that doesn't matter. As long as you have a force and it does work on the body, it changes its kinetic energy. Okay, so the force is general. And in the next slide, in this slide, when we talk about the conservation of mechanical energy, we further assume that the force F is conservative. So now we assume that the force F is conservative. Okay, now this is a special situation. Okay, the derivation we have in the previous slide is general. It's true for any force, no matter is it conservative or not. Now for this slide, when we talk about conservation of mechanical energy, we consider a specific kind of force, which is conservative. Okay. Now, but with a conservative force, if you calculate its work done from x1 to x2 and add a minus sign, then that corresponding to the change in potential energy, right? This expression, if you remember what we say in the last lecture, UP minus UQ is minus the force, the conservative force, integrating from Q to P, right? You remember this relation? So if F is a conservative force itself, then I would have what? I would have the integral of F from x1 to x2 with a minus sign be equal to ux2 minus ux1. That is the potential energy difference between the body at position x2 and the body at position x1. Okay, and I denote it by delta U, the change in potential energy. So that means the two equations can be combined like this, right? We have this integral as delta K, but minus this integral is equal to delta U. So that means delta K plus delta U is equal to 0. And that is exactly the conservation of energy. Okay. Now the delta means a change. So if there is any change in the kinetic energy, say that's kinetic energy loss, that will go to increase in potential energy. So in this equation, the two changes sum up to 0, meaning that with one of them decrease, the other increase. Okay, if the kinetic energy decrease, the potential energy will increase. And vice versa, if the potential energy decrease, the kinetic energy will increase. So the total energy remains a constant. Okay, one decrease, the other increase, but the overall total energy remains unchanged. And that is denoted by the total mechanical energy E. Okay, this is called the mechanical energy. The mechanical energy is sum of the kinetic energy and the potential energy. And that always remains a constant in the motion. Okay. Now you may not be quite familiar with the differential notation like this because I involve the delta here in this equation. But you can always think of the differential, right? The delta is just the D. Okay, you can think of when the delta is getting infinitesimal small, then it's become the derivative. So what I'm talking about is dk plus du being equal to 0. Okay, and from this equation, the differential can be taken out. So differential k plus u is 0. The total change in k plus u is equal to 0. And so that means k plus u must be equal to a constant. And that constant is by definition the total energy E. Okay, so that is the meaning of this equation. Okay. So what is the physical interpretation? Now, we in the previous slide, we confine ourselves to a conservative force, right? So that means if the work is done by the conservative force, it will interchange the potential energy and the kinetic energy, but the total energy, mechanical energy remain constant. And that is called the conservation of mechanical energy. Okay, now so that means what? That means if initially the body is moving at a velocity v1, okay, and has initial potential energy ux1 because it is at position x1, so you have potential energy ux1. This is the initial total mechanical energy. That will be equal to the final kinetic energy plus the final potential energy. So the total energy remain conserved. Now, this is in fact the expression you learned in high school, right? In high school, when you talk about throwing a ball upwards to the sky, you have the kinetic energy, which is half mv squared, plus the potential energy, which is mgh. They added together to be equal to constant, right? And the constant is the total energy. Okay, so you can just move the terms in this equation, delta k plus delta u equal to 0. You can just move the term with all x1 v1 to one side, with all x2 v2 to the other side, and you arrive at this equation that relates the total energy between the object at the two different positions. Okay. At position 1, you have potential energy U1, Ux1, and kinetic energy half mv1 squared. At position 2, you have potential energy Ux2 and kinetic energy half mv2 squared. And this sum of energy always remains a constant. Okay, and that is the total energy. Now, so we can, this formula is general because it's applied to all conservative force. And so we can, when we come up with a problem that involves a conservative force, we may use the expression of U in that problem to help us solve, to help us describe the dynamic of the problem. Say, for example, if we are talking about throwing a ball upwards near the surface of the Earth, that is vertically motion under gravity, we know that the expression of U is mgx, right? The x is the height, right? So we can write U as mgx, and here U will be mgx1 on the left-hand side, and on the right-hand side, the U will be mgx2. The value of U at the first level and at the beginning of the motion and at the end of the motion. Okay. If we are now studying not throwing a ball, but we are studying a block attached to a spring, and the spring obeys Hooke's law, we have the potential energy of a spring be given by half kx squared. And in that case, the Ux1 will now become half kx1 squared, and Ux2 will become half kx2 squared. Okay, so now we relate the velocity and the position of the object at one position to the position and velocity of the object at another position. Now, we haven't solved the whole dynamic of the problem. We cannot find a relationship that describes the position of the object at any time. We don't know about that. In fact, we haven't solved this problem. But somehow we are able to use the consideration of energy to relate the position and velocity of the object at different instants. So that is the idea of using energy. The energy concept does not allow you to solve the whole dynamic. So you do not have a full description of the object position at any time, but still you are able to predict say the velocity of the object at different position. Okay. And if you are saying about a object, say released at a large distance from the Earth, say, and you released an apple at a large distance from the Earth center, say from R1 and let this fall to R2, for example, you just replace the potential energy function by minus GMM over R. So now on the left-hand side, you have minus GMM over R1, and on the right-hand side, you have minus GMM over R2. Okay. Now let us have a simple example for you to understand this concept. Suppose now we have a spring, and the spring is initially stretched to extension of x equal to 0.2 meter. And the spring has a force constant of 3.2 Newton per meter. And the mass of 0.8 kg is attached to the spring. And then the spring is released. So the object is now released from rest with an initial extension in the spring. So I would like to know what would then the speed be a speed of the mass when we reach the equilibrium position. The equilibrium position is the point where the extension is 0 and the force acting on the object is 0. So essentially I stretch the spring, and here I attach the mass, and then I release it. And I want to know what will its speed when it passes through the position of equilibrium. Okay. Now let's apply the conservation of mechanical energy in this form. Initially, the object is released from rest, so V1 is 0. And finally, I know that I want to know its speed at the equilibrium position where x2 is 0. So finally, the object does not have any potential energy. So its potential energy is 0. And initially, the object is released from rest, so it does not have a kinetic energy, right? So now I have this simple equation, which allows me to solve for V2 in terms of x1. x1 is the initial position, 0.2 meter, initial extension of the spring. Km, we know the number, so I can know V2. V2 is equal, eventually I calculate, and equal to 0.4 meter per second, okay? Now let's have a more complicated problem to work on. Suppose you have an asteroid. Have you seen the movie Don't Look Up? There is about an asteroid striking the Earth, right? And suppose when it is at a distance 10 times the Earth radius. Now R, the capital R is the radius of the Earth. Suppose the asteroid is initially at a position 10 times the radius of the Earth from the Earth center, okay? And at that time, the asteroid is moving with a velocity 12 kilometers per second directly towards us. So I would like to know what would its speed, what is the velocity when it hit the Earth's surface, when it just collide with the Earth, what would be its speed? And so because this is a great distance from the Earth's surface, so I should apply the potential energy in this general form. It's GMM over R, okay? Initially, I have R1 be equal to 10 times the Earth radius, while V1 is equal to that's 12 kilometers per second, and I convert it into, because it's km, I now convert it into meter. It's 1.2 times 10 to the power 4 meter per second. And finally, because it's colliding with the surface of the Earth, so the final position is R2 equal to the radius of the Earth R. And I would like to know what is V2. So I substitute all this information into the equation. And I can solve V2 in terms of V1, okay? I rearrange the terms and I solve V2 in terms of V1 and also the R, okay? And here, there's a factor of 1 minus 1 over 10, so it's 9 over 10. And after I take the square root on both sides, I know that V2 is given by this expression. And I substitute the value of G, the mass of the Earth, and the radius of the Earth into this equation. Then I got the final velocity. The final velocity will be 16 kilometer per second, or 1.4 times 10 to the power 4 meter per second. Okay, so that is the answer. Okay. Now, how about this? Let me have a simple version for you. Suppose the object is released from rest at the distance twice the Earth radius from the Earth center. And so what would then be its velocity when it's collide with the Earth surface? Express your answer in terms of G, M, and R. This is a simple question, but just to wake you up. So you got the basic idea, right? I give you 3 minutes to do it. Okay. Now, in case you forgot, I let you have the basic formula first. Okay, you have this, right? MV1 square minus GM M over R1. Don't forget the minus sign. The potential energy carries a minus sign, okay? All right, so work on this formula and see what is V2, okay? Yes. Yeah, both of you got the correct answer. Congratulations. Great. It's good for me to get some response during the Zoom lesson because I cannot see your face. So it would be nice if you give me some response. I would be very happy about that. Okay, thank you for doing that. Okay. So I think maybe some of you have already found the answer, right? So let's work it together. Well, I go back to my pen. So now initially, the object is released from rest, so it is 0 with the initial velocity. And the initial position is what? Is r. It's just a radius, 2r, right? Because we start with this distance from the Earth center. And this is the final velocity we would like to find. And the final position is r, right? Because it's collide with the surface of the Earth. So that means the formula goes like this. I cancel the small mass m, and so it becomes this one, be equal to half v square minus gm over r. If I move this term to the left-hand side, 1 minus 1/2, so it just gives me gm over 2r with a positive sign, right? Is that right? So I cancel the 1/2 on both sides and I take square root of the equation. I find this result. All right. So it's not difficult, right? Now we have go through quite a different kinds of situation. We have go through some different situation, and you might have mixed up those concepts. So I create this infographic to clarify the concept once more. Okay, so that you know what equation applies to which situation. Okay. Now when we first talk about this chapter, when we start this chapter, what we are talking about is a work done by an external force on the system. And that caused the system to change its energy. Okay. For example, when we apply external force, okay, on a spring mass system, a mass tied to a spring, that is called our system. And now I apply a force from the outside, then that is of course external force, right? And in the beginning of this chapter, we find that applying the external force on stretching the spring will cause the work to store up as a potential energy in the spring. So the work goes to the change in the potential energy, and that's half kx squared. Okay, now that's what we introduced to you at the beginning of this chapter, right? But in this lesson, just a few minutes before, I introduced to you another concept. Suppose the object is not tied up by a spring. Suppose the object is free to move. So that the external force will what? The external force will accelerate the object. It will change the speed of the object because it's input energy and the energy goes to a kinetic energy, right? So in this situation, the work done by the external force will go to what? Will go to the increase in kinetic energy. It goes to a change in kinetic energy. So the work done by the force will be equal to half mv2 squared minus half v1 m1 squared. Okay. Now these are the work done by the external force. Whenever you have external force does work, you either input energy in the system or you take away some of the energy. Okay. If the work done is negative, then it takes away energy. If the work done is positive, it input energy into the system. It could be any form of energy. It may be potential energy if you are talking about a spring mass system. It may be kinetic energy if you are talking about an object that is not affected by any other force other than this external force. Okay. But now, how about internal force? How about internal force? The internal force within the system, will change the energy from one form to another. Okay, and in our previous example, we consider an internal force that is conservative. Now, for example, in this spring mass system, the internal force is the force of mass, or the force of the spring. That is the internal force. And the force of the spring is conservative. It is conservative because the force on the spring can be expressed as a potential energy. Okay, and so what causes and what will happen when this internal force does work, when this conservative force does work? Now, because the system is now isolated from its environment, it is not affected by an external force. I'm not moving it. Okay, I just let it to vibrate on itself. Okay, so that means the internal force will thus work to have an exchange in energy between the potential energy and the kinetic energy. Okay, suppose the spring is now being compressed, so the kinetic energy will go to the potential energy. When the spring is being extended, it extending itself, it accelerates the box, so the potential energy will go back to the kinetic energy. So it only leads to an interchange of potential and kinetic energy. But the total energy of the system remains constant because this is an internal force. This is not the work done by an external agent. Okay, so I have the conservation of mechanical energy for this system as delta K plus delta U equal to 0. And if you like, you can write explicitly out K is half mv squared and U is half kx squared for spring. I can also consider, for example, a mass moving vertically under gravity. Okay, and in that situation, the internal force is mg. I now include the Earth also as a part of the system. Okay, so the internal force is between the block and the Earth, and that's just mg vertically downwards. And this force, the work done by this force will cause the interchange between the potential energy and the kinetic energy. The potential energy is mgh when you do it near the surface of the Earth, and the kinetic energy is half mv squared. So the work done by internal force, it will not change the total energy of the system. It will only interchange different kind of energy within the system. Okay, it may change the potential to kinetic or kinetic to potential energy, but it will not change the overall total energy of the system. And that's why you have the conservation of mechanical energy for this system. Okay, is that clear? So when you examine a system from the point of using the point of view of energy, make sure that you know if the force acting on the system is the internal force or an external force, and also the force acting on the system, whether it's conservative or not. Okay, if it is external force, the force will change the energy of the system. If it is an internal force, which is conservative, it will only exchange different kind of energy, but keeping the overall energy remain conserved. Okay. Now we just have a long lecture, so it's time for us for a break with our discussion. Now we go back to this slide. Now, if we know the shape of the potential energy curve, we can actually predict the motion of a body under the action of this potential. Now here is an example. Suppose we have a potential energy curve goes like this. It's a concave curve, and you can see there is a minimum point at the position x0, right? So this x0, according to our previous discussion, it corresponds to what? It corresponds to a position of stable equilibrium. So that means a small disturbance about this point will what? will cause the object to move back to the equilibrium position. So that would be a stable position here at which the object goes at rest. Now we consider a displacement away from the equilibrium position to the point x2. We suppose the object is released at position x2 from rest. Okay, so we just release the object here at this position x2, and we would like to predict how would it move after we release it using the conservation of mechanical energy. Now, by intuition, I think you know the answer. Okay, it's just like a bowl. Okay, it's just like a bowl. You release a marble on the side of the bowl, and the marble will roll down along the slope, right? So it will acquire some speed, right, at the bottom of the bowl, and it goes to the other side. And by conservation of energy, it will not go to a position that is higher than its initial position. Even if there's no energy loss, the highest position that the marble can reach is at the same level at its original position. So it goes to the other side, but goes to the point where it is at the same horizontal level, vertical level at the original position. Okay, and so it stopped there momentarily, and then it slide down again, right? And it goes back to its original position, right? And then it just slide back and forth between the two sides. Assuming no energy is lost, it just slide back and forth between the two sides. It's moving back and forth, and that's become an oscillation. Okay. Now we are going to see the intuition goes like this, right? We know the answer, but we are going to describe it using mathematics more precisely. Okay, so let's see how to do it by using the conservation of energy. Now, we know that the conservation of energy says the kinetic energy and the potential energy of the body added together is always a constant, provided there's no energy loss and no external force applying work to the system. Okay. Now at position x2, the object starts from rest. So you don't have any potential kinetic energy, right? Because the object is released from rest. So the V at that moment is 0. So K is 0 at that moment also. Okay. But you have the potential energy. The potential energy is equal to Ux2, right? So that means the total energy is equal to Ux2. That is the initial total energy. And that energy remains a constant. The E remains constant throughout the motion, right? Now, so you can draw a horizontal line with the value E that intercept the potential energy curve. And that represents what? That represents the total energy of the system. And the total energy is equal to the initial potential energy at the position x2. Okay, so the horizontal line here represents the total energy, while the curve here represents the potential energy. Okay. Now, so what will happen next is that the force acting on this body is now accelerating the body to the negative x direction, right? So the object keep accelerating, and at the minimum value, at the minimum position of the potential energy, its speed is largest. And then when we go to the other side, its speed decrease because it is decelerated by the force, right? So on this side, if the object is accelerated by the force until it reaches the maximum speed, and after passing through x naught, it's decelerated by the force, right? Because when the object goes up, the force tends to pull it back to the equilibrium position. So the speed will decrease here on the other side. Okay. And when it reaches the point x1, which is at the same, with its potential energy at the same value as x2, it comes to momentary at rest. Okay. Now why? Because at x1, the potential energy Ux1 is exactly equal to the potential energy at x2. So that means Ux1 equal to Ux2, and the kinetic energy there is 0 because all the energy goes to the potential energy. So there's no kinetic energy. So that means the body will be momentary at rest here. okay? And then it will slide down. It will act by the force to the right, and it will accelerate to the right, okay? And the process will just repeat itself. The body will just be sliding from here to there, and then go back to its original position, and then go back. And so there will be oscillation between the two extreme points of x1 and x2. So the particle will just oscillate between x1 and x2, okay? And the speed, how do we find the speed about at any point? Now, it's not difficult because we know the total energy. The total energy is E, okay? So we can find the kinetic energy at any position by subtracting the potential energy from the total energy, okay? Because K plus U is E is constant. So the kinetic energy at any point is E minus U, right? But the kinetic energy is what? It's half mv squared, okay? So that means if I move the 2 and m to the right-hand side and take a square root, the V becomes square root 2 multiplied by E minus U divided by m, the square root, okay? Now, what is E minus U? You notice this funny thing. Now, in our graphical representation, the E is a horizontal line, right? The total energy is equal to the initial potential energy. And U is the potential energy curve. So in this diagram, it's become very clear that E minus U is this gap. The difference between the total energy and the potential energy is this distance, is this energy difference, okay? So you can see the V is proportional to the square root of this energy difference, okay? So that means what? That means if E minus U is larger, you have a larger velocity. Is that right? It's simple. Now, so what is the point? Where is the point where the E minus U is largest? Is of course as a minimum position of U. When x is equal to x naught, the position, the energy, the potential energy is lowest. So you will have a largest value of E minus U. So that means the particle has a larger speed, and that corresponds to our intuition because of the body is being accelerated down along the slope. So it acquired the largest kinetic energy at this position. So this is the position, x minus x naught, the equilibrium position is the position where the potential energy is minimum, but the kinetic energy is maximum, okay? So this is the position where you acquire the largest, higher speed. And the higher speed is given by E minus U x naught multiplied by 2 over m square root, okay? So that is the higher speed, okay? Now, in the previous slide, we discussed about the conservation of mechanical energy. You notice the difference in the wording. I do not say we're talking about just the conservation of energy, but we emphasize the mechanical energy, because what we discuss, what we include in the mechanical energy is only two forms of energy: the potential energy and the kinetic energy. We assume that the system has no dissipation. It does not dissipate the energy, so that the sum of the kinetic energy and the potential energy remain constant. Okay, now that is our basic assumption. We do not allow the energy to be dissipated by friction or by viscosity or any kind of dissipative force. Okay, so when we say about the energy conservation in the previous example, we are just referring to a very special situation of the system without energy loss. And in that case, the mechanical energy is conserved, okay? But in the real world, there are dissipative force, right? There are always friction, there are always viscous force, if you or even drag force, if you are talking about a fluid motion, right? Okay, and so we regard these forces as external force. For example, the frictional force may be regarded as an external force that act on the system. Okay. Now, if there's a kind of frictional force as an external force acting on a system, then mechanical energy will not conserve, right? But the mechanical energy of the system will be equal to the work done by the external force. And so in this situation, the frictional force will be doing negative work on the system, and it will decrease the energy of the system. Some of the energy will be changed from mechanical energy to other form. And those other form may include the internal energy, which is heat. And in some situation, in some extreme situation of collision, it may become light and sound. Okay. So whenever there's external force acting on the system, there's energy change. And if the external force is a dissipated one, like friction, there will be energy loss in the system. And the energy loss will go to the other form of energy instead of mechanical energy. It will become heat. Heat is a kind of internal energy. And also it may become light and sound for the case of collision or other dissipated process. Okay. But if you include also this different kind of energy, you will find that the total energy of the whole world, of the whole universe, is always conserved. And this general principle is known as the conservation of energy. Now, the conservation of energy does not depend on what energy you include. You simply include all kinds of energy, and you sum up all the energy, all the different kinds of energy, and you find that in a closed system, the sum of all this energy is always conserved. Okay, but for mechanical energy, for conservation of mechanical energy, you only focus on the potential energy and the kinetic energy. Okay, and the mechanical energy will conserve only if the system is free from external force, is free from dissipated force. Okay. Now let's have an example of having friction in the system. Okay, what would friction cause if the inclined plane has a frictional force acting on the block? Now I project the ball upwards, then what will happen? The frictional force will dissipate some mechanical energy. Okay, now suppose now I have an inclined plane, inclined at an angle theta to the horizontal, and now I have a block of mass m. It is initially at the base of the inclined plane, and it's projected with a velocity u upwards along the plane. Okay, so the initial velocity of the block is u, and it's along this velocity is along the inclined plane. But there is a frictional force. The coefficient of kinetic friction between the block and the plane is mu. So I would like to find how far the block will travel, the distance that the block will travel before coming to rest. Okay, eventually the block will somehow either momentarily rest or at some point on the inclined plane. I would like to find out that position. That is our problem. Okay. Now, in order to calculate the friction, we first have to resolve the force component along the direction that is perpendicular to the inclined plane. Now we know that there is a normal reaction coming from the inclined plane on the block, and that component I call normal reaction I call R, right? But since the block is not moving along in the direction perpendicular to the inclined plane, the normal reaction R must be balanced by the by component of gravity mg cosine theta. Okay, so R is equal to mg cosine theta because there's no motion in a direction perpendicular to the plane. So the component along this direction must be balancing each other, and so R is equal to mg cosine theta. So the frictional force, as we know, is equal to mu R, where mu is the kinetic friction coefficient. I skipped the subscript K, but it's understood that in this situation it's referred to the kinetic friction. the frictional force is the mu multiplied by the normal reaction. So it's become mu mg cosine theta. Okay. Now, after finding the friction, now we are ready to apply the conservation of energy. But in this situation, there's external force. The external force is the friction, right? It transforms the mechanical energy into heat, into internal energy. Okay. So we apply the work energy theorem. If we regard the frictional force external force, then the work done by the friction will cause a change in mechanical energy. And the change in mechanical energy is equal to the final mechanical energy minus the initial mechanical energy. Okay. Now, how do we express the work done by friction? Because we know that in the whole process, the frictional force is being a constant given by mu mg cosine theta. So the frictional force just does the work corresponding to the frictional force multiplied by the displacement. The displacement along the plane, I call it S. That is the maximum displacement along the plane. Okay, so Fs is the work done by the friction. And I deliberately add a minus sign here because I know that the work done is negative. The block go up, right? But the frictional force is directing downwards along the plane. So it does negative work. And what we mean by negative work is that it decreases the energy of the system. The work done by the frictional force decreases the energy of the system. Okay. And you can also understand it by taking note that the direction of motion of the block and the frictional force, they are in opposite direction. So that's why there's a minus sign. Okay. The work done by the friction is equal to what? Equal to minus mu mg s cosine theta. Okay, we simply multiply F by S with a minus sign. And how about the change in mechanical energy? The initial mechanical energy, if you assume the base of the inclined plane as a reference position, then at the reference position, we don't have potential energy. So the only kind of energy at the base is the initial kinetic energy, which is half mg squared. So we have initial mechanical change of half mu squared. But at the top of when the block goes to the maximum heights, its kinetic energy is 0, right? So it becomes momentary at rest. The only energy that the block has is the potential energy. The potential energy is mg multiplied by the height that it has traveled, but the vertical height is the displacement multiplied by sine theta. So the height is s sine theta. So we have mg, the height, which is s sine theta. Okay. And the difference between the final and the initial mechanical energy is equal to the work done by friction. Okay. Now, so we arrive at this simple equation. Okay. Now our M is to solve for S. So now we move all the term with the S to one side and we extract a factor of S. And the mu square, I put it on the other side and all the M are cancelled. And so rearranging this factor to the right, I got S equal to U square over 2G sine theta plus mu cosine theta. So that's our answer. Okay. When we talk about energy, it seems to be a method of solving the problem, which is quite different from Newton's law, right? Now, energy consideration allow us to predict some future properties of the system, for example, velocity, without solving the dynamic of the intermediate step. So you see, in the previous example, we haven't solved the whole problem. We don't know where the object is and what is its velocity at an arbitrary time t, right? We haven't solved the differential equation to get the position and the velocity at any time, right? So we haven't solved the dynamic of the whole problem. But even with the energy consideration, we are still able to predict some future properties of the system, like for example, its velocity at different time. Because when we know the total energy of the system and we know the potential energy term, we would know the velocity of the system at different position. That is some information about the system, even we haven't solved the whole problem. Okay. Now, in some situation, it may be quite difficult to solve the differential equation of motion. It's not that easy, but still we can use the energy consideration to tell us some information about the system. So that's why the conservation of principle is very useful. And I would let you know, I will let you see in the next slide that conservation of energy and Newtonian equation of motion, they are just a different formulation, different mathematical formulation of the same physics. Now, it's important to note that the mechanical energy conservation is not a new thing. It is not different from Newton's law. It is not a separate law of physics. But in the classical regime, in the classical mechanics ideas, the two concepts are actually related. And I can actually derive the principle of conservation of mechanical energy from the Newtonian equation of motion. Okay, now let's see how these two formulations are related to each other. Now on the left, you see the Newtonian equation of motion. The second derivative of the displacement with respect to time is acceleration. But in Newtonian physics, the acceleration is the force divided by the mass, right? So the acceleration is known. If we know the force, net force acting on the object, we know the acceleration. And for the conservative system, the acceleration is a function of position only. It's independent of velocity. Now you can see this equation is a second order differential equation in time, okay? Which means that it involves the second derivative of x with respect to t. That is so-called the second order differential equation. Now, how about the conservation of mechanical energy? The conservation of mechanical energy is half mv squared, which is the kinetic energy, plus the potential energy U, E being equal to a constant, the total energy E, right? And we may write the velocity V as a first time derivative of the position. So V can be written as dx dt, right? Now, using this equation, I can solve for dx dt. I move the U to the right-hand side, it becomes E minus U. I multiply the equation by 2 and divide by m, take the square root. I solve for dx dt. Dx dt is equal to this guy, right? Now you can compare the equation of motion in these two forms. On the left-hand side, if you start with Newton's second law, you have a second order differential equation. You have to solve x, right, from a second order equation, which involves the second derivative of x with respect to time. But for the energy formulation, you notice that you still have a differential equation because the left-hand side is dx dt. But now the equation is reduced to first order because it's involved the velocity only, but not the acceleration. The velocity is dx dt, the first derivative of x with respect to time. Okay, so the difference is between the Newtonian formulation and the mechanical energy formulation is that the first one is the second order equation. The second one is the first order equation. So when I go from the second order equation to the first order equation, effectively I have done an integration, right? If they are the same formulation, but just different form, I go from the second order to the first order, I have essentially done an integration. Now you may wonder where I've done the integration. Now I guess you go back a few slides and you will see. Now when I start with the Newton's law here, when I derive the energy theorem for the kinetic energy, okay, I multiply both sides with what? The dt. And we convert the v dt to dx. And we integrate both sides, right? So what we've done here is exactly an integration. Is that right? So what I'm doing here is an integration. I integrate Newton's second law, not with respect to time, but with respect to x, to obtain the principle of conservation of energy. In fact, that's what we are doing. So effectively, when I go from Newton's second law to the energy conservation equation, I just do an integration. I've just done the integration. The integration with respect to x. Okay. So I change the second order to the first order equation. Now, but doing integration must mean more of an integration constant, right? And the integration constant is to be determined by the initial condition. So where is the integration constant here? You will ask. I would say the integration constant is the total energy E. The total energy E is an alternative way to specify the initial condition. Now, when we talk about Newton's second law, when we solve this equation of motion, we emphasize that we need the initial position and the initial velocity to fully specify the motion, right? And those are the initial conditions. Now, with the energy formulation, the initial condition is somehow specified in an alternative way. It is not specified with respect to the initial position or the initial velocity. It is specified in terms of the initial energy. So the energy E is sometimes called the first integral of integral constant of the equation of motion. Some people say call it like this. Okay, and it's in fact the kind of initial condition introduced to the system. It tells you that how much energy that the system processed initially. Okay. If you like, you can go to this. We have taught you in the lecture. But if you like, you want to go to higher dimension, you need to learn line integral. The line integral is a way to calculate the work done by variable force in 2 or 3 dimensions. And you also have to learn about curl and gradient if you want to express a conservative force. If you want to check whether a force is conservative, and if you want to check whether if you want to derive the force from the potential energy, you need to learn about this differential operators such as curl and gradient. Okay, but these are beyond the scope of this course, so I put in an extension. If you like, you can click on this link to read about this. These are simple narration given by Professor Kenneth Yang. Is give you a very quick but holistic summary of what we should do in higher dimension for work and energy. This is the comprehensive discussion on the work and energy in higher dimension. Okay, so I leave it to you as a self-study. I would not go into the details because it's an introductory course. I don't want to stretch you too much on this complicated maths. And the last part of this chapter is about power. Now, what is power? Power is a rate of doing work. Okay, it is not just work, but how fast the work is done, so to speak. Okay, so let's derive an expression of power from Newton's second law again. Now, in this situation, we can work with Newton's second law in higher dimension. So we do it with a vector form. So F vector is equal to m dv dt, where v is a vector. Okay. Now we would like to form a dot product between the force and the velocity. So F dot v on the left hand side is equal to mv dot dv dt. We just form a dot product of the equation on both sides of the equation with the velocity v. Now let's see how we handle the term on the right. Now we can handle the term on the right as half mv dot v, the time derivative. Okay, you just treat it as V square. So when we differentiate the V square, we just get T2V dV dt, right? But the 2 will cancel with the 1/2 here. Okay, so I can write this expression as half mv dot v, which is half mv square. Okay, now you can see immediately that this is the rate of change of kinetic energy, because half mv square is kinetic energy. So dk, the kinetic energy dt, is the rate of change of the kinetic energy. So something, the work is done at the rate so that it changed the kinetic energy at a certain rate. That is the meaning of this equation. So that means the force is now changing the energy of the system at the rate, and that will go to the change in kinetic energy, the rate of change of kinetic energy. Okay. So that means we can interpret the F dot V as a power, the rate of work done by the force. And so power is given by F dot V. And because if it's a rate of work done, the work done has a unit of joule. The rate of work done will have a unit of joule per second. The work done per unit time, right? Because this is the energy done per unit time, the energy transfer per unit time. So it has a unit of joule per second. Okay, and formally we call it a watt. A watt is by definition joule per second. Okay. Now, why are we interested in power instead of just work done? Do you know the answer? The power actually give us the rates at which the energy is delivered. In some situation, you need to deliver energy really fast. For example, if you run up a stair, okay, you may be walking like an old man. You may walk up a staircase in 10 seconds, right? So you are delivering your power very slowly. But to walk up 10 seconds, to walk up the stair of a certain height, you need a certain potential energy, which is independent on whether you do it fast or do it slow, right? The energy is the same because the height of the staircase remains the same. But if you can do it fast. If you are young, then you can exert the energy very fast. You can output the energy very fast. And so you can develop a large amount of energy in a very short time. And that is the power. If you are an old man, you may be walking up the stair in 10 seconds. But if you are young, you may just need 2 seconds to go up the stair. Okay, you deliver the same, you both deliver the same amount of energy. But for you are young, so the time for you to required for you to deliver this energy is very small. So you have developed a high power. Okay, because power is the energy divided by time. So the shorter the time of delivery, the higher the power you develop. And that is the physics of the term power. Okay. Now there's also another joke. Okay. Do you like eating chocolate? Who like eating chocolate? Consider a bar of chocolate of about say 20 grams. I don't know, a few tens of grams. Okay, you do not eating the chocolate. Now, a bar of chocolate actually contains more energy than the TNT explosive of the same weight. If you consider like a bar of chocolate with 50 grams, okay, in mass, and that exactly contains much higher chemical energy than a bar that is made of the explosive, TNT explosive, the industrial explosive. Okay, but if you use a bar of industrial explosive of 50 grams in magnetic explode, it will destroy the whole classroom. Okay, but you can never destroy the whole classroom with a bar of chocolate, right? Now that's sounds to be a joke, but in fact that's the case. If you look up the amount of energy in a bar of chocolate, that will be higher than the total amount of chemical energy stored up in the same weight of TNT. Okay, so why is it different? Why a bar of chocolate cannot blow up the whole classroom? The reason is, for chocolate, you eat it, and your body digests it, and eventually your body will slowly digest the chemical energy inside and release it slowly for your body use. But that process is very slow. So the power developed by eating a packet of chocolate is actually released very slowly. So the power is very small. Although the energy is large, but the power is very small. But for the explosive, okay, the same amount of energy is released in 1,000th of a second during the explosion. Okay, so the power is high. And from this equation, if the power is very large, that involves a large force or a large velocity. So in the explosion, the pieces scatter with a high force, large force, and with a large velocity. And that causes a causality, right? And that's caused destruction of the room. So that is the difference between power and energy. A power causes destruction if it's not properly used. Okay, so that is an interesting thing about power and energy that you might haven't heard of. I just want you to have some understanding of the basic physics behind all this mathematics. Okay. So we end this chapter, and I would have a brief introduction to you on the chapter of momentum. Maybe I will only have a full discussion with you next time, but I just can introduce to you several important aspects of momentum in this course, in this lecture. Now, what is momentum? Momentum actually measures the impact effect of an object. Okay, you know that the momentum is the mass multiplied by the velocity, right? So if you have a large object, the impact force you expect the impact force will be large if it impact on you, right? If the object is small but still is moving at a high velocity, then you also expect the impact force to be large. So the impact result, the impact harmfulness of a body is measured by the impact power is measured by the product of the mass and the velocity, and that is the momentum. Okay, so that is the idea why we developed the concept of momentum. Now let's see a single particle first. Now Newton's law says that F is equal to m dv dt, but since m is a constant in Newtonian physics, m doesn't change. We can always make mv together. We can always put the m inside the time derivative because it's always a constant. It does not affected by the derivative. And we call the combination mv as a linear momentum or simply momentum. Now we emphasize this is a linear momentum because when we talk about rotation, there's another kind of momentum that's associated with rotation, and that's called angular momentum. So here we emphasize the momentum is in a linear form by using the word linear here. So the linear momentum is defined mv. And in terms of the momentum, we find that Newton's second law can be formulated as the net force acting on the body being equal to the rate of change of momentum of the body. Okay, so that is another form of writing Newton's second law. Now, if there is no net force acting on the body, then momentum will be conserved. Why? Because when F is 0, dp dt is 0, right? And if P, the time derivative of P is 0, it means that P is a constant. And that means the momentum is conserved. And of course, for a single particle, it corresponded to the situation where the velocity of the particle doesn't change, right? So that means the velocity doesn't change or momentum conserved, okay? In vector form, we have the force equal to the rate of change of momentum also in the vector form. And that involves also the change in momentum, magnitude itself, and also the direction. Momentum has a unit of the mass multiplied by the unit of velocity, right? So it has a dimension of m, while the dimension of velocity L(t minus 1), so it has a dimension of L m L(t minus 1). And SI unit is of course kilogram meter per second. Now let's talk about the system of two particles before letting you go. Now this is quite interesting as it's closely related to Newton's second law and third law. Now let's consider a very simple situation of two blocks moving together along a frictionless table. And the block 1 is being pushed by force F, okay? Now, so we draw a free-body diagram of the two blocks. For block M2, the only force acting on it is from block M1, right? So I call it R. The R is the normal force between the two blocks. So R is the force due to M1 acting on M2, okay? So when I set up Newton's second law, it becomes R equal to dP2 dt, where P2 is of course the momentum of the block M2. Now for the block M1, we of course have the external force F, but there is a reaction force from the block M2, right, acting on block M1. And the reaction force of course has the same magnitude R due to Newton's third law, right? And so the free body diagram tells us that the net force will then be the F minus R because the two forces are on different direction. The net force being equal to dP1 dt, where P1 is of course the momentum of the block M1. Now let's add the two equations together. We have now two equations, right? And let's add them together. Now we notice that when we add the equation together, the R will cancel. The internal force cancel. And so what we find next is the following. We find that the total force acting on the system is equal to the rate of change of P1 plus P2. Okay, not just P1, but not just P2, but it's equal to the rate of change of the sum of P1 and P2. And we can call this sum the total momentum, capital P. So here we have a very interesting form of Newton's second law. The Newton's second law now applies not only to a single body, but to two interacting bodies. And no matter how the two bodies interact, the internal force will always cancel. This R will always cancel with this R, right? Now I have this particular example of pushing the two blocks, but you can imagine they are not interact in this way. Imagine they are gravitational body interact with the force of gravity, or you may imagine them to be pulling each other, right? As long as Newton's third law holds for the two bodies, the internal force always cancel when we sum up the equation of motion of the individual free body diagram. And the result is that the overall result is independent of R. And we find that the external force acting on the system as a whole will always be equal to the rate of change of the total momentum, not just the momentum of individual particle. Now this is very important because we have successfully extend Newton's second law to more than one particle. Okay, when we write the Newton's second law in terms of momentum and using Newton's third law, we are able to express Newton's second law as a system in the form of a system of particles. Okay, so P is the total momentum of the system, summation Pi. Now the similar argument can extend to an arbitrary number of particles, in fact. Okay, if you have many particles interacting with each other, no matter how complicated they interact, as long as the interaction obey Newton's third law, you always have the external force acting on the system to be equal to the rate of change of the total momentum of them. So the internal force just exchange the momentum. When one particle acts an internal force on the other, it loses some momentum, but it transfers the momentum to the other particle. So if you look at the system as a whole, the momentum will not be affected by those internal force. Only the external force does matter. And that's exactly reflected from this equation. Only external force will change the total momentum of the system. And so this is the form of Newton's second law for system particle. The rate of change of total momentum of a system is equal to the net external force acting on it. Okay, and in simple, we write F as dp dt, where you remember P is the total momentum, not just a single particle, and F is the sum of all external force. It is not just the force acting on particle 1. There may be force acting on particle 2 also. You just form a vector sum of them, and the net, that is the net external force acting on the whole system. Okay. And if the external force is zero, if there's no net force acting on the system, then the total momentum is conserved. And that means the summation of the individual momentum, because this is the definition of total momentum, remain constant. So the internal force are there. The internal force may change the momentum of the individual particle, right? But as long as there is no external force, that internal changes will not change the total momentum. If one particle loses some momentum transfer to the other, the total momentum still remains a constant. And so summation of Pi is equal to a constant in a system without external force. So in the absence of external force, the total momentum of the system is conserved. And that is a statement of conservation of momentum. Now, in the next lecture, I will talk about it in more detail, in more mathematical terms. But I use this very simple example just for you to understand the physics behind. The momentum conservation for a system particle hinge on the Newton's third law. Okay, because the Newton's third law, the momentum transfer from one particle to another is always conserved for a system of particle. Okay, so that means the Newton's third law saves the momentum conservation. Okay, so let's stop here. I think time is up. So let's stop the recording.